Point your phone at a houseplant, and in milliseconds, it identifies the species. The classification happens instantly and entirely on device, processing the complex visual data without needing to ping a remote server for help. Yet, the most capable artificial intelligence models, the ones powering complex text generation and deep reasoning tools, are built on hundreds of billions of parameters. They demand massive amounts of computational power to function. To house that kind of scale, these models typically live inside sprawling data centers, running on racks of specialized servers. That reliance on the cloud creates real hurdles. If you lose your internet connection, you lose the AI. And routing sensitive, real-time data back and forth to a distant server introduces privacy risks and unavoidable latency. You might think we could just retrain an existing model to fit a new device. Transfer learning allows developers to teach a model new skills, but it doesn't actually shrink the physical footprint of the code. The resulting model remains massive. Engineers have also tried chopping away the least used connections, a process called pruning, or downgrading the mathematical precision of the calculations, known as quantization. These methods trim the hardware requirements, but they delete information in the process. They chop up the physical network without transferring the underlying wisdom the model originally learned. In 2015, Geoffrey Hinton and a team of researchers at Google proposed a different approach. Instead of trying to aggressively compress the physical hardware structure, they looked for a way to extract and transfer the knowledge itself. Fitting a data center in your pocket without sacrificing its intelligence requires moving beyond physical code compression. Engineers must instead teach a tiny blank slate model to mirror the internal logic of a massive one. This is knowledge distillation. Think of the original massive cloud model as a master chef and the tiny edge model as a novice apprentice. The chef has spent years processing billions of ingredients to learn how flavors interact. The goal is to pass that intuition down to the apprentice. Standard machine learning trains a model using what are called hard targets. These are strict binary labels. If the model is looking at a picture of an apple, it is told 100% apple, 0% orange. That right or wrong feedback provides extremely limited context for learning. But our master teacher evaluates data with much more nuance. Instead of a binary answer, it produces soft targets, a spectrum of probabilities revealing that multiple different answers might actually be partially correct, based on its vast experience. This chart shows the distribution of raw scores, known as logits. For an image of a handwritten number 5, the master teacher produces a primary spike for that digit, while simultaneously calculating specific probabilities for every other category it knows. It might calculate a tiny chance that the image is a sloppily drawn 6, and an even smaller chance that it's a 3. It knows with absolute certainty that it is not a car. These nuanced relationships between the incorrect answers, the way the model generalizes the data, is what researchers call its dark knowledge. To make this dark knowledge easier for the student to read, engineers apply a mathematical parameter called temperature. Increasing the temperature softens the teacher's rigid confidence. It flattens the curve, pushing those near-zero probabilities up so the tiny student model can clearly study how the teacher weighs different options. The student can be trained to mimic the teacher's final probability output, known as response-based distillation. Or, for a deeper transfer, it can map the exact way the data moves through the teacher's internal processing layers, which is called feature-based distillation. By mathematically transferring this structural logic, instead of forcing the apprentice to blindly memorize correct answers, developers have successfully compressed state-of-the-art models by up to 70 times, all while maintaining their advanced reasoning capabilities. We inevitably run into the physical realities of silicon and memory. When you map a network of 70 billion parameters onto a model with only 1 billion, you cannot preserve every detail. Knowledge distillation creates what researchers call a lossy projection. The apprentice is an imitation. It acts like the master chef, but it is not a perfect one-to-one clone of the original model. If the teacher is simply too vast, a tiny student physically lacks the architectural space to absorb the knowledge. This is known as the capacity gap, and when it happens, the smaller model's performance rapidly degrades. There are also inherited risks. Because the student is designed to mimic the teacher's exact behavior, it absorbs the flaws right along with the wisdom. It will replicate the teacher's biases, adopt its hallucinations, and repeat its errors with high confidence. This creates significant intellectual property and privacy concerns. Distilling a closed-source, proprietary model into an open-source framework means that sensitive training data and hidden algorithms can unintentionally leak into unregulated public applications. This chart illustrates how we evaluate these apprentices and why those tests can be misleading. A student might match the teacher's benchmark accuracy, looking like a perfect copy. But beyond that primary metric, severe gaps emerge. The student often loses the teacher's safety guardrails, nuance, and reliability. Relying solely on headline accuracy hides these invisible losses. Knowledge distillation democratizes artificial intelligence, bringing the capabilities of supercomputers directly to the devices we carry every day. But because that translation is lossy, it leaves us with the strict responsibility of testing, verifying, and monitoring these apprentices before letting.
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.